Okay, this model is a little bit strange because this is a list of models. We don't go through together because there's there's no meaning that I kind of babble about things. The models that we are going to see in this module here are going to be ODEs of physical systems that are being recalled every now and then as examples. The first example is RC circuit. For the people that do not feel like having the intuitions about electrical systems, I forgot the name, mechanical equivalent of electrical systems. Where was it? This one. This is super interesting because in a certain sense, they are toys that you can use to kind of convert the equivalent of electrical circuits in mechanical circuits. And watch this video. I think it should be able to make you feel very confident, or at least more confident, about interpreting this and about how to interpret this one. In the handout, there's all the derivations, so read them out. I assume that you know about electronics enough to be able to somehow describe this type of systems. Okay, let's go back just a moment. Here we have something that generates a certain voltage, so it's our motor, true? And we have a certain tension here, and our VC is what we want to control, and the dynamics are in terms of changing the voltage. The voltage will not change immediately, depending basically on C and R. We are going to have. If I want to make, let's see if we're together. I have this system here. Let's assume that we know how to derive the equations. If I want to make the system faster, and this one is given, what shall I do? And why? If I can change other things and I want to make the system faster, and the unique other thing that I can change is going to be the resistance. True? What shall I do? I want to make the system faster. That means in time, this is my U. If I change my U like this, my VC is going to change like this. True? To make the system faster means I would like a system that does like this. True? What shall I do? This one shall go to 0. The less resistance the system has, the less inertia the system has. True? Okay? What's up, people? Just a call for those systems here. You've got to have intuitions about them. Okay? You need to have the intuitions about those systems that are there and very fast, and they are prerequisites. You should know this. Okay? Are we aligned? Same for this one. Okay? Here we have two elements that are dynamic. So we are going to have a two-order system, second-order system. We are going to have basically this and this. This is our baseline. This is going to be our this is going to be our y. This is going to be our y dot, and this is going to be our y2 dot. Very important generalization. We are going to use very often linear time invariant systems and we are going to write things in a matrix notation. In which sense? We are going to have, for example, position velocity, and we're going to do position dot velocity dot is equal a position velocity plus force, or u, some transformation, bu. And if we have more stuff, we are going to have something that is bigger in dimension, but we are going to have matrices. Okay? For example, here we have it. True? Let's rewrite it as matrices. We have y1 dot, that is y1 dot, is going to be equal to 0, 1, y1, y2. y2 dot is equal to minus 1 over LC minus R over L, and then there's going to be a plus 0, 1 U, 0, 1 over L, sorry. Together, you see how I transform the equations from a line to a matrix? How much are we together, people here? 1, 2, 3. Okay. What is this one? The same. True? The same. Isn't it the same? From a structural perspective, those two are the same, people. Do you notice that they are the same? From an equations perspective, we have position dot is equal to velocity. There we have integral of the current dot is equal to integral to the current dot. Why is this notation very useful? Because at a certain point of the course, we will abstract ourselves from the various physical devices, and we are interpreting them as matrices. But they are going to mean different objects. Why are we cybernetics people very much wanted by the industries? Because we can jump between industries very easily, because eventually we abstract ourselves from the ODE, we get the mathematical nature, and whenever we abstract ourselves, the MPC, the stochastic MPC, for example, is going to work the same code that you do for a mechanical system is going to work for the electrical system. You will have some domain expertise to understand some curves here and there. But you see how lifting ourselves from mechanical slash electrical slash biological slash societal to math and working here means that I get application domain 1, application domain 2, application domain 3. We lift into math. We work here, and then if we want to change job, we go to another place, and we are kind of very ready to go. Together. There's something strange with this connector. No, but we are going to see it next Wednesday. I don't want to invest time to see something that we're going to see again. Lotka Volterra, we're going to see. This one is a model that we are going to see very often. So I do not show this one because we see it next time. Those ones are the equations that we saw last time. True. So prey and predators. This is interesting. This is another system that is very much interesting, and we are going to use it quite often. This is a simulator of a clock. We are going to see the face, whenever we do face portraits, we discuss about why it's a clock. This model here, remember the name, Van der Pol simulator, Van der Pol equals to a clock. We will see whenever we do the face portraits. Okay? For the people that know what linearity means, is this one a linear model? Yes, no, I do not know. No, why? there is this stuff linear? Very much no. This one, is it a linear model? Yes, no, I do not know. Very much no. This one, is this one linear? It's bilinear. It's called bilinear. Okay, it's not linear, non-linear. Together, we will see linearity very much. Segway, physical system that has got two objects, the mass here and the mass of the wheel. Okay, so how many state variables are going to be there? 4. Position and speed of this, position and speed of this. True? So we are going to have something that is more complex together. We are not going to derive it. There's the derivations if you want, but there's no sense. It's kind of an example of a linear time invariant system. True, false, I do not know. The question is this one linear? Yes, no, I don't know. We call that cosines and sines, very difficult that it's linear. True? Are we together? But this is another example. This is a series of models that we are going to use during the course. At home, you go reading what they mean. If you do not have intuitions, you try to develop intuitions so that whenever we call them out for making examples, we know what we are talking about. Okay? Perfect. Insulin. This is a model, a basic model of how insulin reacts. Whenever you eat something, your glucose will change and your insulin will change, levels will change. It's a switching system. This is maybe the unique thing that I've got to say. Depending on where you are fasting or not, depending on whether you are hungry or not, your body reacts in a different way. This one, there's a typo. There's a typo. I think, sorry, it's this one and this one. How is it possible that there's a typo? No. Depending. Oh, no, it's not a typo. No, it's written in a bad way, but it's okay. This is the dynamics of the insulin, and this is the dynamics of sugar. If you're hungry or not, you have either this couple or this couple. You see? Slightly different. Your body reacts in a different way depending on the state it is. This means that somehow x1, x2, x1 dot, and then we have, in this zone, we have a certain dynamics. And in this other zone, we have another blanket. You see? And the two blankets will meet each other. See? Point? This is called a switch system. Depending on where you are, you follow a y dot. Okay? You see it, people. 1, 2, 3. 1, I see. 3, I don't see anything. It's the generalization of x dot. Here we have, I don't know, a quadratic. And here we have a line. You see? Multidimensional. This one we did enough. Let's do this exercise. This model here should be sufficiently. We should have been discussing this sufficiently well, so that you can find which parts of this paragraph is correct or wrong. Go and discuss. Okay, people. Am I giving too little time? Maybe yes. Somebody that points out one error. Somebody that wants to point out one mistake here, please. Excellent. This is an error. The other one, there's another one. So the population dynamics, the predator population is dependent also on the population of the predators, not only on the availability of prey. True? Together? And there's another one. The growth rate. What is the growth rate? Rabbits dot is equal to alpha rabbits plus. This is the growth rate. The growth rate is that alpha. That alpha doesn't depend on R. That alpha goes multiplied by R. We will see that the notation is essential. This type of exercises, I tend to like this type of exercises because they make people kind of think a little bit at stuff. The growth rate is going to be the time constant. We're going to see it. Okay, questions about the stuff that we did up now?
The second error you mentioned after the SOLI, what was it? Because I'm not sure if I catch it.
So the growth rate is alpha.
Yeah, no, yeah.
And alpha doesn't depend on R.
Okay.
Alpha gets multiplied by R, but the growth rate is how much time it takes for the population to double. To double, we will see whenever we do time constants that it's going to be something that is independent on the actual number of rabbits, but it's only on the growth rate alpha. Other questions?